Uh, Hello, everybody. Yes, as I've been introduced, I'm Lorena. I can talk a bit about me. I'm Spanish, but I've been living in Denmark since 2013. I did my PhD in Barcelona in Spain, and then I moved to Denmark. I started working as a postdoc at the ITU, and it was there that I started working and doing research on electronic elections, and that is my topic today. And I also have some experience so as a software developer, IT security consultant. Right now, I'm a teacher at KEA, at the Copenhagen Airways Academy, where I'm teaching at the professional, one of the few professional bachelors that we have here in Denmark in IT security. And well, in particular, this semester, I'm teaching on applied cryptography and also in software security, two courses of the education. So this is the agenda for today. I will start with a bit of introduction of what e-voting is and what online elections are in this context. We will also talk about some of the components, the most typical components that we find in e-voting software. And also I will finish my presentation with some, let's say, some real life e-voting systems that have been used. In particular, this one has been used in Norway. So we talk, when we say e-voting systems or e-voting software, what we mean is actually any kind of election, any kind of voting process in which we are using electronic systems or just technology in general. So there are mainly two types. The first one is the one in which there is still a polling station, people still go there physically, but then there is a machine that helps you in casting the vote and also in counting and doing the final tally of the results, like what we see here in the picture. And another type, another kind of electronic elections is remote voting, that is also known as online voting. The one in which we vote from home and using internet and using some browser or also a mobile phone or whatever. There have been many places, many countries where e-voting, internet voting in particular, has been used already. In some places, it is still used with kind of a success, let's say. In some others, it has been stopped for various reasons. For instance, in France, it was used for many years for citizens living abroad, so that they could participate in the elections anyway, but it got discontinued since 2017. We also have that in Norway, they were doing a couple of pilots in 2011 and 2013 for local and national elections, but then it also got discontinued. In Estonia, they've been using it since 2005 and they are still using it. This is one of the few places where it's still being used and it's still considered a success. In Spain, for instance, it has only been used in a few internal elections, but only within specific political parties. So it hasn't been used in bigger election processes. In Lithuania, for instance, they had plans to use it this year. They had national elections at the beginning of October. In the end, it was not in a general sense an internet voting election, but they gave the option of voting remotely for those people who were living abroad and also people that were self-isolated because of the COVID-19 pandemic. Among the arguments that we find people in favor and against e-voting, supporters' arguments are that elections that are online are cheaper, are easier. That means that it's also easier to just have even more elections. They are also quicker, they are also reliable, and it's kind of highlighted because, as we will see, this is kind of a challenge, this reliability of election results. It is also thought that the fact that you are providing more channels from which you can vote, it will increase voter turnout, but it hasn't been really proved that this is the case. It also, it's also said that it improves access to voting process, people that have disabilities, in a secret way, because usually there is someone that needs to go inside the polling booth to help the people with disability. The idea with e-voting is that this should be possible to be done, alone, with no extra help. Then some of the arguments it brings voting in line with new developments in society. It's like it's what everybody expects, because we are using new technology in all aspects of our lives, and people are also expecting that in electronic processes and election processes. And it's also expected to help into avoiding casting malformed ballots, because we expect the software or the machine to help us into voting as it's supposed to as we are expecting them to vote, in terms of the format, in terms of what is a valid ballot and what it's not, and so on. Among the opponents' arguments, we find the risk of large-scale manipulation. It is thought to be easier to manipulate the results, both by insiders and also outsiders. Difficult to detect. So if there are source of errors, if there are bugs in the software, any kind of technical malfunction, people think that it will become much more difficult to find where that error is coming from. Also the need for additional voter campaign, because even though we are trying to kind of translate the same process, e-voting processes are meant to be like the equivalent of a traditional voting process, but just online. But in reality, it's not like that. It's not that direct translation. And then that means that we also need to kind of teach citizens into using these new methods. And that also means that people might be losing some trust that they already had in the traditional voting process if we all of a sudden do everything online. The last reason from opponents' views is one of the curious things that we found out when we were doing research on e-voting here in Denmark, where when we were kind of considering whether people would be interested in e-voting, having the possibility of voting remotely from home without having to move and go to the polling booth. Citizens were saying that they would really miss meeting their neighbors on election day if they had to stay at home, no matter, regardless of the bad weather or rainy days or whatever. So now, if we want to build a voting and e-voting software, and of course we want it to be secure, there are a few considerations that we need to do as in any software. First of all, of course, we are expecting the software to have in consideration some list of requirements, what the software is expected to do, the functionalities that we are expecting the software to have. We will also expect to do some kind of risk analysis process where we take into account all the risks, all the threats that might be involved in the software. Then from that, we expect to extract some list of security requirements, and we will see what that is in the context of e-voting. And all that taking into account security design principles. Security design principles are kind of guidelines that help us into evaluating how to design software if we were to build software from scratch, or when the software is already existing, to evaluate the security of that software. So there is a well-known list of the security design principles, but the ones I'm going to mention here are just the ones that are relevant in the e-voting context. The first one, for instance, is simplicity. As in any problem, we would like to find the simplest solution, because the simpler solution means that it's also easier to understand, easier to be reviewed, easier to find flaws if there exist such flaws, vulnerabilities, yes. Open design, security design principle, is the one that is, is what we have in cryptography. It's known as Kerckhoffs's principle. The idea is that whatever the security mechanism that we are going to implement in our system, we want to make this mechanism public, so that everybody should be able to just have a look at that, try to understand how they work. And we expect that by being open, then people might end up being able to understand the system and also eventually trust it. This is what open source software, for instance, is embracing. Minimum exposure. So for this, we mean reducing external interfaces to a minimum. We want to reduce the possibility of attacks from an attacker, from a potential attacker, or minimize the window of opportunity for an adversary to attack in terms of time, for instance. Minimum trust. So it's not that we are against trust, but it's that we should be seeing trust as something that should be gained. So it's something that you can, you don't want to take for granted. You want to check that everything is all right before starting to trust it. So for instance, when there are a few parties interacting, and from one party we get input from, one party gets input from another party, we don't want this party to just trust that it's gonna get only valid input. We just want to check all input, and in case if it's not valid, then take the necessary measures. Complete mediation. So all the checks should be consistent, and there should be no other possible paths to their resource. Like for instance, yeah, this funny picture, right? No single point of failure. Make sure that there is more than one protective layer. This is also something that we applied in e-voting systems. Usability. This is one of the most important ones, even though it doesn't look like at first sight. No matter which security mechanism we are implementing, if we don't manage users to, if it's so difficult to be used that people, that the users are not going to use it anyway, or that they might end up misusing it, or just circumvent it so that it's not used correctly, then it won't be worth at all. So it's something that we really care about. We want e-voting systems to be usable as possible. And the last one, not that there are no more, but these are, as I said, these are the most relevant ones for the e-voting context. Promote privacy. So we are not going to gather all source of information from users, so from citizens. We are just going to try to gather all necessary information related and relevant to the election. So now from here, we can extract, let's say, a list of security requirements that any e-voting system is expecting to have. In terms of integrity, we are expecting the outcome to match the voter's intent. And that can be divided into individual verifiability and universal verifiability. Individual verifiability is what any participant in the election should be able to prove or to check. That the vote was cast as intended, that it was recorded as cast, it was counted as recorded. Whereas universal verifiability is what anybody, even people not directly participating in the election, should be able to verify or to check. And this is the case, for instance, of the tally. So anybody, even though I'm not the one voting in an election, it should be possible for me to just go there, look at the result, and be convinced that everything was fine and that the tally is correct. Eligibility. So only people expected to vote, so that are allowed to vote can vote. Privacy, so nobody can figure out how a voter votes. Receipt freeness, a voter shouldn't be able to prove how she votes, and this is very much related to coercion resistance, because if I cannot prove how I vote, then chances that I will be coerced are also lower. So no party should be able to force another party to vote in a particular way, and that also includes to be abstained from voting. Fairness, so we don't want partial results to be revealed before the election is finally over. And of course, there are many other requirements, maybe not that much related to security. But there are a few issues. Some of them, the issues are, for instance, the compromise between election verifiability, that is integrity, and ballot privacy. So I'm sure you agree with me that if we do some kind of hand-raising process, then it's completely verifiable in the sense that we can just count how many hands are raising up, and we can see who's voting for what. So therefore we can check that the tally, the final result of this election, let's say, is correct. But then of course, this is not private, right? Because we are seeing who's voting for what. On the other hand, if we want to prioritize this ballot privacy, we can imagine some system, kind of a black box system. We don't really know what's going on there. Everything is using maybe some standard crypto, but again, we don't know. We have no way of checking that that is really the case. We might say that this is private, but then of course, how do we check the tally? How can we be convinced that the tally is really correct and really reflecting the voters' intent? So this is one of the challenges, one of the compromises that we find in e-voting systems. Anyway, privacy needs to be achieved somehow, and the best way to achieve it, or the typical way at least in e-voting, is to encrypt ballots. So this would be in relation to this complete mediation design principle. Ballots are encrypted. How are we going to encrypt them? The typical way is not that it's the only way to do it, but the typical way is using asymmetric cryptography. So there will be a public key and a private key, both of them generated by election authorities. The idea is that whenever a voter wants to encrypt his or her vote, we will take the public key and just encrypt it. Whenever we want to decrypt the votes and therefore count compute the final tally of the election, we will use the private key to decrypt those votes. The encryption algorithm, there have been many encryption algorithms in literature. Can be El-Gamal, can be Kramer-Shoup, there are many others. The typical one has been El-Gamal. But now one of the questions is, how do we secure this election private key? That is the key that we need to use to decrypt the final result, or at least to decrypt each one of the ballots and therefore compute the final result. One might think that maybe we can encrypt it, but then again, we also have a key to protect. We might think of maybe duplicating the key, but that might not be that secure, right? So the idea or the problem that we face here is that we don't want the whole privacy to rely on one single person. So the election authority having this single private key that is the one having the power to decrypt all the ballots and therefore compute the final result. We want to avoid having just one person with that much power. So this would be this no single point of failure design principle that we've mentioned. How can we solve this? This is secret sharing, which has been already mentioned in the previous talk by Bernardo. And I will just go briefly through it. So the idea is to distribute the key to a group of people in different shares, and none of these individual will actually have the key by itself. So this is also known as a KN threshold scheme. N is the number of parties and K is the threshold, is the minimum amount of shares that need to be gathered so as to recover the secret key. An example, not that much related to elections, but just so that this concept of secret sharing is understood. We may have a president of a company having 3 shares, a vice president, we give him 2 shares, other officers, CCO, COO, CTO have 1 share each. Now, given this distribution, if we use a 3N secret sharing scheme where 3 is the threshold, we have that the following groups, any of the following groups, will be able to reconstruct the key. It can either be just the president on its own, the vice president together with any other officer, or any 3 officers. So it's a way of distributing the power of this key, who is going to be allowed to reconstruct the key. In e-voting systems, the typical secret sharing scheme used is the one known as Shamir's KN threshold scheme, which is based on polynomial interpolation, where each one of the shares is a point in the graph. And of course, it has the dealing phase and reconstruction phase. Some of the properties that it has, probably one of the most interesting properties is that it's information theoretically secure. That means it's completely unbreakable. So it's not something that depends on how much computational power an attacker has, but it's just perfectly secure. So if you have less than k, less than the number of threshold shares, then there's no way for you to guess or find out what the secret key is. The problem, one of the problems, is that shares are not verifiable, which means that people having the shares can just submit fake shares, and therefore that prevents reconstructing the key. But luckily, in the literature, we can also find some other solutions to that, like this Feldman scheme, where this secret sharing scheme becomes verifiable. Some other properties that makes this scheme quite flexible. We can increase n, so the number of shares that we are going to distribute. We can just add new shares, and that without affecting the new ones, the ones that have been already generated. We can also remove shares, still without affecting the existing ones. We can also replace share, either all of them or just k of them, so the threshold of them, periodically, so in a regular basis, without changing the secret. And this is what is called proactive security. So this would be in relation to this minimum exposure design principle, in which we want to reduce the time of the window of opportunity to the attacker, so that doesn't have that much time to try to find out the key. It also needs a dealer, so it needs someone who is in possession of this secret key and then distributes the corresponding shares. But there is also a distributed version in the literature that is the one actually used in e-voting. So now we have a way to protect the votes so that they are secret or confidential. This is by encrypting them. We also have a way to keep the election key, this private key, safe. We are going to secret share them among a group of election authorities. And this is how the voting process looks like right now. So, of course, the first step would be to generate these election key pairs. Then this private key is shared among election authorities. Voters encrypt the vote using this public key, as I mentioned before, and then send them to the ballot box or the bulletin board. And in the end, when the election is over, election authorities gather, reconstruct the secret key, decrypt all the encrypted ballots, and then just compute the final result of the election. Are we done? Well, now we are going to see that there are a few steps that need to be improved. For instance, as you can see here in these steps, we have to decrypt ciphertext one by one before counting. And of course, that is not good in terms of privacy, because then that means that we may get information about who's the one voting for that candidate. How can we solve that? Again, this is a concept which was mentioned in the previous talk, homomorphic encryption. The idea of homomorphic encryption is that we will be able to compute, to operate on encrypted data without having to decrypt that data first. So in e-voting, that means that we have ballots encrypted in the bulletin board, and we are going to be able to compute the final tally just using this encrypted version of the ballots. Of course, the result will also be encrypted. We will have a result for each one of the candidates. And in the end, once the election is over, is when we will be able to just decrypt this final result for each one of the candidates. Therefore, we are not decrypting each individual ballot, but we are just going to decrypt each one of these final results for per candidate. Let's say more technically, this is done using an additive homomorphism. Since, as I mentioned, at least for this example, we are using this ELGAMAL encryption algorithm, it turns out that we can slightly modify this algorithm so that it has this property of homomorphism. So we have a message, we can encrypt that message, we do the same with a different message. It turns out that with this modification, if we multiply these two ciphertexts, the result is the ciphertext of the corresponding sum of the plaintext. So by just multiplying the encryption of the messages, we get also the encrypted results. So now, if we look again at how the e-voting process ends up in using homomorphic encryption, we have that voters encrypt their vote using the election public key, then send it to the bulletin board. Then an encrypted final tally is computed from the encrypted ballots using homomorphic encryption, and then election authorities join their shares, recover the private key, and then decrypt the final results. So now we don't need to decrypt each of the encrypted ballots one by one. But now what happens if the election authorities decrypt individual ballots? They can still do that, right? So they can just go here, this step, and before using homomorphic encryption, try to decrypt these individual ballots. And since these ballots have been sent to the bulletin board, the order in which they were recorded, that also might be linked to the identity of the citizen sending that ballot. So one way of removing this link is by using mixing, or by using mixnets, which are a set of servers, so different nodes. Here we see this would be like different ciphertexts, different encrypted ballots. Each one of these nodes is going to re-encrypt the ciphertext so that they look different, and they are also going to shuffle them so that they are also recorded in a different order. That way, we are going to miss this link that we had at the beginning of the order in which these ballots had been recorded in the bulletin board. So now this e-voting process gets updated again. At the end of the election, a mixnet re-encrypts and permutes the ciphertext. So therefore, now even if election authorities went and tried to decrypt individual ballots, these ballots at least will look different, and they won't have any relation. It won't be possible to link them to the citizen sending each one of these ballots. But there is still one more issue. How can we make sure that everybody is actually following the protocol? We see that the protocol, I wouldn't say is simple. There are many steps and there are many parties involved. So how do we make sure that everybody is following the protocol and not misbehaving? For this, there is also one tool in cryptography that is called zero-knowledge proof of knowledge that ends up being quite helpful. In any proof, there is always a prover who wants to prove something to a verifier. So wants to convince of something, of some statement being true. Just a simple example, if I want to prove that this number, 38,477, is not prime, how can I do it? How can I prove that it's not prime? You might be thinking of many ways, but definitely one of the ways is that I tell you the factors, right? If I tell you what the factors are, you know that you take both factors, you multiply them, you get the number. Therefore, that means that indeed this number was not prime, right? But we have a problem here. And this is actually not a good example of zero knowledge proof of knowledge, because you got some knowledge. So you didn't only got convinced that this number is not prime, but you also learned the factors, the corresponding factors. Therefore, this is not zero knowledge. So the idea, what we want to achieve with zero knowledge proof of knowledge in e-voting is to be able to convince someone that a statement is true, but also in a way so that you just learn that the statement is true, but nothing else, no other extra information whatsoever related to that proof. In practice, what we use in e-voting is something called Sigma protocols, which can be made non-interactive. So by that, I mean that it's not an interaction between a prover and a verifier sending challenges to each other and replying, but it's just something, it's just a set of steps that anybody can verify afterwards. So there is no interactive, there is no interaction, sorry. The properties that we expect from zero knowledge proof of knowledge, the ones that we are going to use in e-voting, is completeness. So whenever the statement is true, we expect the verifier to always accept the proof. Soundness, which means that if the statement is false, then the verifier should reject with high probability, which means that there is still a slight and small probability that it won't be rejected, but should be small enough. And zero knowledge, so the verifier shouldn't learn anything beyond the validity of the statement. How do we measure, what do we mean by gaining knowledge? We define gaining knowledge by the fact that, so the verifier is said to learn something, to gain knowledge, if he or she is able to compute things in a more efficient way than before the interaction. So for instance, in this example that we saw before about factors, we expect to factorize a number to be something really, really inefficient, especially with bigger numbers. But with this way, with this kind of proof that I gave, the verifier is also learning the factors, therefore is able to do things that he or she wasn't able to do before I told him what the factors were. So this is how gaining knowledge is defined. Now, where do we use, or where are we expecting to use zero knowledge proof of knowledge in e-voting? It is expected to be used in different places and by different actors. For instance, we are expecting every voter to generate at least one zero knowledge proof of knowledge, proving that the encrypted vote contains a valid value. Since it is encrypted, it's nothing that we can check, that anybody can check, because it's encrypted and we will have to decrypt it to be sure. Therefore, it's something that only the voter can prove. Of course, it needs to be zero knowledge. Why? Because we don't want the voter to reveal what the content of the vote is. Otherwise, it wouldn't make sense to encrypt it in the first place, right? Election authorities are also expected to generate zero knowledge proof of knowledge, proving that the decryption is correct. So by that, we mean that the private key is the good one. That means the one that decrypts what the public key was encrypting. And also that the value claimed as the election result is the one that really corresponds to the ballots that are in the bulletin board. And what is the zero knowledge part? So what is it that we don't want to get, that gets revealed, is this election private key, of course. We don't want anybody to be able to get access to this private key, not even at the end of the election. And also every mixnet. So remember that these mixnet nodes, each one of them is going to apply re-encryption and a permutation of all the ciphertext, of all the encrypted ballots. So we want each one of these nodes to prove that this re-encryption and shuffling is correct. So it is really re-encrypting and really shuffling. And by that we mean that, for instance, we are re-encrypting so that we are not changing the content of the encryption. So the plaintext remains the same. It just looks different. It just has a different randomness involved. And what is it supposed to keep secret or to not reveal the permutation itself, for instance? We don't want them to reveal the permutation, but it does need to be a permutation. So now, somehow we are, let's say, done with the cryptographic part. So once all the software is built, of course, we are not done. If we care about security of an election, we are still expecting these processes to take place, not necessarily in this order, but some code reviews, which usually is static code analysis, but it can also be dynamic code analysis, penetration testing, some security operations involved, maintenance, certification, and so on. So there are many things that we need to be careful about in these processes. And it's really, really difficult. And I can give you an example of something that they did. It's this real life e-voting system that they used in Norway. the system was, the name was EVA. As I mentioned at the beginning, Norway used internet voting for local elections in 2011 and parliamentary elections for 2013. In particular, I was observer of these last elections, the ones in 2013. The interesting thing of it is that it was done as a supplement of paper-based voting. So during 2 weeks, people were allowed and encouraged to use online voting. And then they still had a specific election day in which they could still go physically to a polling booth and then vote there on paper. So it was, both things were done at the same time. The steps that this system had was, first of all, citizens were asked to register their mobile phones with some kind of a registry. And then after that registration, they received on normal postal service some list of return codes that were different for each citizen. Each one of these codes was in association with a candidate. And the idea of these return codes was to provide this cast as intended verification, so that they could check that their vote went actually to the citizen that they intended to vote for. Then, when the citizen was ready to vote, they would access a JavaScript website. So they could see the process here starting. Then the voter was presented with authentication services. So they could use this min ID, which is the equivalent somehow to our name ID in Denmark. Then it was expected to select the choice. So here's where we see all the candidates. So it just selects the candidate. And then it asks, at this point is where the citizen receives in his or her mobile phone an SMS with a code. That code is the one that the citizen needs to check and match against these return codes. If it's the same, it means that everything went fine. If it's not, then something goes on and then they need to file a complaint. The next step is when the voter was presented with a hash value of their encrypted ballot. So of course you may, you need to have in mind that this was what all citizens in Norway were seeing. So that means you can imagine people being familiar with the concept of a hash function, but of course there were also many other people who didn't know what a hash function was or what it really meant for them to see a hash function. So I'm shown a hash function. What does it really mean? What do I need to do with that? It wasn't that clear, right? Or it could have been not that clear. The idea behind that was to provide some kind of a store as cast verification, because then afterwards you could go online to a GitHub repository, which ended up being like 4 gigabytes of file. You could just download that. That was the bulletin board. And the idea was, or what you were expected to do was to look for this hash value in the GitHub repository and check to see whether your ballot was there. Then when the election was over, there were 3 steps. So first one was cleansing the ballot. So it's when they really need to check the ballots that need to be counted. So remember that we are doing online voting first and then paper ballot voting. That means that we need to identify which one is the one that counts. If people were voting more than once online, then only the last one was the one that counted. If people were voting more than once, but then on the election day they went and vote physically on the polling station, then that paper ballot was the one that counted. So therefore, all this was taken into account here in this first step of cleansing. So it's really identifying which are the ballots that really need to be counted and discard the rest from the same citizen, of course. Then mixing, using mixnets, and finally the e-counting process, which was done on air-gapped computers and yes, checking all the zero knowledge, proof of knowledge, and so on. This phase was also including something that they called the decryption and counting ceremony that I will mention later. So some of the properties that we can see from this system was in an attempt to have a coercion-resistant system, they were allowing this repeat voting. So as I mentioned, you could vote more than once, but then if you went, only the last one was the one that counted, and if you vote on paper, that's the one that counts over the online ballot. It provides individual verifiability, cast as intended, store as cast, because of this hash of the encrypted ballot. Universal verifiability, so anybody, even people not from Norway, not participating in the elections, could just go there. They had this zero knowledge, proof of knowledge accessible for everyone. They were public. You could just go there, download them and check them. Of course, also for that, you also need to have the necessary background and knowledge to know what to do and what to really check. And also fairness, because they were implementing secret sharing. So they distributed among, so they were a total of 9 shares of the private key of the election distributed in the election authorities, and 6 was the threshold. So 6 was the minimum that need to recover, that need to gather, join their shares and recover the corresponding secret key. Now this is the decryption and counting ceremony. In an attempt to make the process as visible as possible, as transparent as possible, they made a public event in the ministry where they were using these overhead screens, and they were showing the Linux commands where you could see how they were decrypting, how they were doing the checks. So here in this small screen, they were doing the checks of the zero knowledge, proof of knowledge by a team that was called the verifiers. They even tried to make visible the process of destroying sensitive information, and they did that by using a blender and destroying, physically destroying the USB sticks there. And even to kind of symbolize that people were drawn at random to come to the e-counting machine with their share of the secret key. So for that, they were using a top hat with names on it and so on. So it was really interesting to be there. I was there in the public and see all the efforts that they were doing to try to make the whole process more visible. And at least they were hoping to get people trust the process more. So as a conclusion, so we can see that e-voting is really a true reality in some countries. It has been a reality in some countries and now it's not. In some others, they are still using it. But there are still a few things that need to be improved. Because the idea is that they want to replicate the same functionality. We want to have a voting process that looks as much as the traditional voting process, so that people don't need to learn new things. But then with computers, this becomes really complex, and there are many places where things can go wrong, and then we need to kind of patch and start using tools that not everybody understands, and not everybody has the knowledge to know how it works. So everything becomes really difficult to observe. So you know that in real life, in paper-based voting, anybody can just volunteer and go there and observe the tally process, whereas this is not something that happens with electronic elections. And still there are many things that need to be checked. So it's not only the source code, not only the software itself, but it's also the compilation, its deployment, the execution environment, so where this software is going to be executed. There are many things that really need to be in place and need to be checked at runtime. And of course, in the end, all this may end up affecting trust in the election process. So yeah, it's really, really an issue. So that was all from me. And yes, thank you.
So thank you, Lorena, for the very nice talk. And there are already 2 questions in the chat. Of course, if people have more, please write in there. I'll start reading the ones that we have. So in the first one, there is an observation and a question. And they say that another argument against the e-voting is that citizens need to understand the entire election system in order to trust it. And I think you already went through this in the final consideration. So the comment is, are we now supposed to turn every citizen into a cryptography expert?
That would be ideal, but of course it's not realistic. And that's actually the issue, that we are, since we want to translate the same processes or similar processes to what we have in real life. And when we do this, in real life, we just have a ballot box with paper ballots. We just do like this, and then everything is shuffled. If we want to have the same process with computers, then is when we end up using some kind of a bit more complex tools from cryptography. And of course, people don't understand that. And we try to understand, to explain, and we make everything visible as much as we can. And we make everything open source, yes, but still we need people that understands that. So that's really the issue as I see it.
Yeah, in order to build trust in the process, you also need to build trust in the experts that verify the process. And,
yes,
it's
indeed.
hard to fight against something that is just physical and people can see and touch.
Yes,
yes,
I agree.
And another question is about the penetration test mentioned after the part on the zero knowledge proof of knowledge in e-voting. And in particular, if the process is properly encrypted, and then what kind of penetration test would be expected?
From the zero knowledge proof of knowledge?
Yes, so let me read it again. So the question is about you mentioned penetration test when you were discussing zero knowledge proof of knowledge. Right after that, I don't remember exactly which slide. I think it was around 28-ish.
Yes.
And the question is, if the process is properly encrypted, then what kind of penetration test would be expected?
Yes, of course, encryption is one part, is where we want to achieve this confidentiality or secrecy of ballots, but that's not everything, right? So we may still have encryption in place and have other ways to break into the system and then have everything broken. So that's why I was mentioning penetration testing, and actually in some cases, penetration testing were allowed even in real live elections. So elections were already running and people were encouraged to try to break into the system and try to even change election results. In some others, well, of course it wasn't allowed, but we expect them to have done their proper tests before everything was run in production. So that's what, that's what I was referring to.
Okay. Now there is a very long question. And a comment. So just a comment based on post speculation regarding the first question and Lorena's response by Fabrizio Monteri. So maybe we could educate people a little on cryptography in high school, like some countries do with programming. Making people understand a few principles usually makes them much more confident when using systems that build on these principles. Teaching the basic principle of homomorphic encryption in a school, for instance, doesn't seem too far off.
Yeah, I think that would help, definitely. Yes. I don't know, in some countries that might be a challenge because of the level at high school, at least what they are expecting to learn. But yet I'm definitely agree that might help. Yes, of course. I'm very much onto that. Yes. I hope it can be done at some point.
Yeah, I mean, it sounds like a solid way to build trust and at least can have familiarity in what are these tools behind all this machinery.
Yes.
And I have a question, if there are any other questions or comments from the audience.
Of course.
Something that I think was a bit in between the lines during your presentation, but I would like to hear a bit more, even if it is a bit technical. If you can comment a bit on the importance of forward secrecy in this process, and what are the risks and how the solutions that are already in place deal with this.
Yes, maybe you can elaborate on what you mean exactly for forward secrecy.
So essentially the problem of with the passing of time and the increasing availability of computational resources or maybe new techniques, then there is the possibility that somebody that has recorded the voting process could go back and break the secrecy and tie back people to the vote they cast. And maybe there is a risk for retaliation or targeting people or in certain, I don't know, situation of political uncertainty. So
Yes.
I wanted to know what is the situation here and if you can comment a bit more on this.
Yes, there are already some solutions. They haven't been implemented, at least not in real life elections, like official binding elections. But in the literature and also in, in the community, research community, there are solutions in which they talk about this everlasting privacy. So it's actually about that. It's about preventing, so to have privacy forever. So that not even in the case of encryption algorithms being broken in the future, then privacy shouldn't be broken at that time. So definitely there are solutions into that. They are not implemented, I mean, in real life as systems. They are using commitment schemes, which are, perfectly secure.
Thanks a lot. And I still have a lot of questions, but well, maybe there are 5 minutes. I would like to, if you can comment a bit on how was the perception of from the public about the experience with the voting you described in Norway. So, because, I mean, well, from your description, it looked like a well prepared and concerted effort with a lot of communication with the public. How did it went? How was the reaction of the public in general and at large?
Well, the public was very heterogeneous. So of course, people having some computer scientist background could almost follow all the process because of course they were showing all the commands. We were totally aware and familiar with the Linux commands and we knew what they were doing. But at the same time, because we knew what they were doing, we were also aware of the risks and how easy it is to, for instance, change a command so as to end up doing something different to what we are expecting it to do. So in a way, I had the impression that the ones knowing what was going on weren't convinced of the correctness of the system, of how everything was going on. And the ones that didn't have probably the necessary background weren't convinced either because they couldn't understand what they were seeing. So they were shown a few command lines and they couldn't understand what that really meant, even though they tried to explain and everything was, as I said, made visible. But of course, the fact that they are destroying a USB stick on a blender, that doesn't mean that the data is not somewhere else.